Hello, welcome to another module in this massive open online course. And in this module, we want to look at yet another important application of least squares, and that is in machine learning in the context of what is known as linear regression, right? So, we want to look at another very relevant and modern application of least squares in the context of machine learning, which is essentially what is termed as linear regression. And as I have told you, this is a very important application in the context of or in the area of machine learning or ML. Now, what is linear regression about? To put it simply, linear regression is basically prediction of a response using, right, these are technical terms, prediction of a response using what are known as explanatory variables. Prediction of a response using explanatory variables, right? What is the meaning of this? So, let's illustrate it using a simple plot. So, let's say you have a lot of data, and clearly you can see this data are correlated, right? So, what I can do is, so this, let's say I denote by x and y. This is what I am calling as my explanatory variable, and y is what I am calling as response, right? And clearly you can see that the explanatory variable and the response are highly correlated, right? One, that is, knowledge of the explanatory variable can help you predict the response of the system, and this can be done, as you might have already guessed, by fitting a model through this, and this is essentially your model, or what you are terming as your linear model, right? So, we fit a linear model so that given any new exclamatory variable, one can predict, right, one can obtain an idea or estimate of the response y hat, right? This is essentially what regression is, that is, prediction of the response using these explanatory variables, and this is essentially trying to fit a model, or in this case what is a linear model, and this is essentially termed as linear regression, right? You are fitting a linear model to the explanatory variables to predict the response of the system. And you are trying to learn this linear model, and that is the example, and that is essentially what the machine learning aspect is about. All right. So, this is essentially the linear model, as we have already stated. So, this is a linear model. So, put it more precisely, you have a response which is y. We are calling this as the response of the system. There are many things, or you can call this as the output. You can also call this as the observation, or you can also call this as the dependent variable. All right, all of these are essentially all right. And then you have a set of explanatory variables. So, you have x1, x2 up to xn and these are your explanatory variables. These are the explanatory variables, and now, or these are also your independent variables, right. So, these can vary independently, that is the idea. So, you have the dependent variable, that is y, these are essentially your independent variables. Okay. So, we have the dependent variable and these are the independent variables, and now your regressor is essentially, your predictor is given as y equals theta naught plus theta 1 x 1 plus theta 2 x 2 plus theta n x n plus. So, this is your regression model. So, this theta naught, this is a fixed term, this is essentially a constant, this is termed as essentially your bias term, or essentially this is also termed as the intercept. Okay. So, this is termed as the intercept, and these theta 1, theta 2, theta n, including, you can also call this as theta naught, these are your regression parameters, or these are your regression coefficients, and this epsilon is, this is your error. You can term this as your error term, or your or essentially your disturbance term. So, essentially your y is given as the sum, the linear combination, right, a weighted linear combination of your explanatory variables, right. So, theta naught, which is the intercept, plus theta 1 times x 1 plus theta 2 times x 2, so on up to theta n times x n, plus your epsilon, where this quantity epsilon, this is essentially your modeling error, or this is your disturbance, all right, and these thetas are essentially the regression coefficients, all right. So, I can write this essentially as y equal to, it's not very difficult to see, 1 x 1 x 2 x n cross theta naught theta 1, so up to theta n plus epsilon, or the error, and this essentially you can denote this by x bar transpose, and this I can denote by the vector theta bar. So, I can write this model in a compact form as x bar transpose theta bar plus epsilon. Okay. And these, again, as I already told you, this theta bar, this contains the regression coefficients, and naturally now the prediction response can, for any unknown, so given x bar, given the independent variables x bar or the explanatory variables x bar, once you know the model, response y can be predicted as y hat equal to x bar transpose theta bar. All right. So, this is essentially your prediction. Okay. So, this is essentially the prediction corresponding to the a new. So, once you fit the model, once you determine the regression coefficients theta bar for any set of explanatory variables, all right, or for any particular explanatory variable vector x bar, the response can be predicted as y hat equals x bar times theta bar. But it is important to first determine these regression coefficients, right. So, that is the thing that has to be done, because if theta bar is unknown, then it is not possible to predict. So, one has to determine these regression parameters theta bar. So, how to determine that is the question. Let us look at some examples, some applications of this. As I have already told you, this is very important, linear regression. It has several applications. For instance, you can have y in the context of y, this can be the price of certain stock, right. This can be price of a particular stock. Y can be the price and x1, x2, xn, these are the explanatory variables. These can be the prices of related stocks. These can be prices So, determine y, that is the price of a particular stock that you are interested in, from, or predict the price of y, that is a particular stock, from the prices of x1, x2, xn, which is essentially you can think of it as a stock market index or a basket of related stocks, right. So, this is essentially a stock market, a stock prediction, stock price prediction problem, right. This is one of the examples of application. So, one can determine y using a linear regressor in terms of the explanatory variables x1, x2, xn, which are the prices of related stocks. All right. So, this is a stock market prediction problem. This is a stock market prediction application. All right. So, another interesting application could be a sales prediction. So, y can be, for instance, sales of related objects, such as, for instance, you can think of sales of SUV vehicles, and x1, x2, xn, these can be, for instance, sales of related objects such as, for instance, x1 can be sale of cars, x2 can be sale of bikes, and it can also be other things, such as, for instance, xn can be the average income or GDP or so on, average income of an area or average income of a particular city or town, right. So, if the average income is higher, naturally the demand for SUVs or demand for vehicles is going to be higher. So, all these, so there is also, one has to also choose these explanatory variables carefully, so that these are related right, sufficiently correlated and can be sufficiently good indicators of the response. All right. So, this is essentially an application of your sales prediction or it is also termed as forecasting. Sales prediction or forecasting. Okay. And another interesting application, again a finance application, this can be for instance your portfolio risk. What is the risk in your portfolio? And your x1, x2, xn, these can be various related parameters or various related quantities such as for instance interest rates, or these can be for instance your interest rates, exchange rates, or stock prices, etc. Now, the question, as we have already said, so this is again a portfolio optimization problem or a risk optimization. Or a portfolio risk optimization. Okay. Now, once again we can ask the question, remember, how to determine the regressor coefficients theta bar, because if you know theta bar, then given any explanatory variable vector x bar, one can predict the response y. Now, for that we start with a set of training data, that is responses and corresponding explanatory variables. So, we start with, the answer to this is start with training data, that is you have a bunch of y bar y1 x bar 1, right, one set of training data, and then you have y2 x bar 2, so on, and then finally you have ym x bar m. So, this is your m points or your set of m training data vectors or training data samples, right. And now, one can again construct the model. So, I can write y1 as, well, theta naught, this is the first training vector, theta naught plus theta 1 x1 1 plus theta 2 x2 1 plus so on and so forth theta n xn1 plus the error, which I can write of course in compact form as once again 1 x11 so on xn1 times theta naught theta 1 so on up to theta n plus epsilon error 1, which is essentially, you can think of this as x bar transpose 1 times theta bar plus the error. Okay. Similarly, one can express y2 as x bar transpose through theta bar plus the error, and ym the mth point as x bar transpose m. So, these are your regression, models, or these are basically the corresponding model for the output. So, now you can write this as the vector y1, y2, ym, as we always do, write it in compact vector notation as I have already told you, and this is where the linear algebra comes in. X bar transpose 1, x bar transpose 2, so on, x bar transpose m times theta bar plus epsilon bar, which is the error, comprises of the errors epsilon 1, epsilon 2 up to. So, this is essentially your y bar, this is essentially your matrix X, which contains the training vectors of explanatory variables. This is your vector x epsilon bar, which is the error, and therefore, I can write this as y bar equal to x theta bar plus e bar, right. So, this is the model, or this is your model for the training data, all right. So, these are basically the regression outputs corresponding to the explanatory training explanatory vectors, the explanatory training vectors, and the training responses, all right. And now, the idea is to determine the theta bar which gives the best fit for, or which gives the best fit for y bar, that is, determine theta hat as the best vector theta bar, the best set of regression coefficients that minimize the error between the training responses and the explanatory or the training explanatory vectors, right. And now, you can naturally see this is again a least squares problem, this is again, and you can now immediately see how powerful the applications of least squares can be applied anywhere via this linear regression model, can be applied now anywhere in sales prediction, stock market forecasting, portfolio risk optimization, so on and so forth. So, theta hat again is given by the solution to the least squares problem, that is, it is given by x transpose x inverse x transpose y bar, all right. So, this is essentially your theta hat, which is your or we can simply call this theta bar, which is your regression coefficients, or you can also call this as the regression parameters, all right. So, therefore, thus essentially one can use once again the least squares paradigm, right, that we have developed so far, and determine the regression parameters or the regression coefficients theta bar, which essentially includes which essentially is basically the vector. If you remember, this is the vector theta 0, theta naught, theta 1, theta 2 up to theta n. So, it also includes that intercept term theta naught, and therefore, now you can see regression or linear regression. This is a very important aspect of machine learning, which in turn has several applications in various areas, such as for instance stock prediction, sales forecasting, portfolio, housing price prediction, traffic prediction. Wherever you can think of prediction, forecasting, or basically determining a response or getting an idea of response based on a set of explanatory variables which are highly related to this response, right, one can use linear regression. And naturally, in all such areas, the least squares paradigm that we have looked at. Of course, linear algebra has a very important role to play, and in particular the least squares can determine the particular regression model by essentially determining the regression coefficients or the regression parameters. And once you define, and I mean once you determine the regression coefficients or the regression parameters, that in turn gives you the regression model, right. So, essentially least squares can be used to determine the regressor, right. Okay. So, therefore, it is again one of, as I have already told you, a very, very important concept, that is this problem of least squares, and solution. The least square solution has wide ranging applications. We have looked at yet another application of the same in the context of machine learning and particular linear regression. So, let us stop here and continue this discussion in the subsequent modules. Thank you very much.